Greetings and welcome to Unit 2, Lesson 2, where we're going to simplify expressions. We're going to carry forward from the last lesson where we talked about functions, function notation, evaluating functions. And if we have functions that involve exponents, you need to know how to simplify them. And if those functions are polynomials, you need to be able to identify them and certain characteristics about them, as well as being able to add, subtract, multiply, and divide polynomials. So this video is going to address the first part of this essential question: how do properties of exponents help me simplify expressions? And then in class we'll talk about what we do with polynomials to help us simplify expressions. So if you think about the basic property of exponents, it means repeated multiplication written in exponential form. So what does a to the fifth mean? Well, since 5 is a counting number or a whole number, we would take a times itself 5 times. So a times a times a times a times a. If I have -4 times -4 times -4, I can write it in exponential form more efficiently as the opposite of 4 raised to the third power. And then if I evaluate that, -4 times -4 times -4 also means -64. If I have 2x to the fourth, it means I'm going to take 2x times itself 4 times, and 2 times 2 times 2 times 2 is 16, and x times x times x times x is x to the fourth. So I would get a final answer of 16x to the fourth. So exponential notation, when a is the base and n is the power or exponent, and n is a number that is a counting number or an integer that is greater than or equal to 1, it means I write that base n times and multiply. And here are your properties or laws of exponents. So here are our 3 multiplication laws. Let's look at the first law. I have a to the m times a to the n, and that equals a to the m plus n. So what that means is that if I have the same base raised to different powers, where the operation between those two is multiplication, I'm allowed to write the base once and add the exponents. So if I look at a concrete example, if I have 3 to the second power times 3 to the fourth power, not plus, but times, I don't get 9 to the sixth power. I can't multiply 3 times 3 to get 9. I only get 9 if it's 3 to the first times 3 to the first. But I can write the base of 3 once and add the exponents to get 6. Let's look at our second multiplication law. Notice in this case I have one base, a, raised to the mth power, and that is raised to the nth power. This is a power to a power rule, so I'm allowed to write the base once and multiply the exponents. So an example is if I have 3 to the second power, and that is raised to the fourth. Notice how the exponents are stacked on top of one another, and I have one base. My final answer, I write the base of 3 once, and I multiply my exponents to yield 8. The last multiplication law involves 2 different kinds of bases. So if I have a, b, and that quantity is raised to the mth power, it is really not mathematically correct to call it the distributive property. The distributive property requires 2 separate operations of multiplication over addition or multiplication over subtraction. But each base is entitled to the exponent that's on the outside. So if I gave you a concrete example that is 3x to the fourth, the 3 gets to the fourth power, which yields 81. And x also gets the fourth power, leaving me with 81x to the fourth. So I haven't done every kind of example, but in order to simplify, if you have any coefficients, you want to multiply them. You multiply your variables using your laws. Deal with any exponent on the outside first. And don't forget in the last law to also raise the coefficient to the indicated power. If there's going to be a mistake, that's where I most often see them. Now let's talk about our division laws. Our first division law is if I have the same base, I have a to the m over a to the nth, so different exponents, and the operation between them is division. I'm allowed to write the base once and subtract the exponents. So you have that relationship of multiplication and addition going together and division and subtraction going together. Here's a concrete example. If I have 4 to the 6th power over 4 to the 2nd power, I can think of it as 4 to the 6 minus 2, and get 4 to the 4th power. Now, we already discussed for the summer skill set, but as a review, negative exponents are reciprocals. So if I have a to the negative mth power, it does not mean that my answer is necessarily negative. What it means is if the base is living in the numerator, it now would live in the denominator as a positive exponent, or as you see in the next law, 1 over a to the negative n, if the negative power is living in the denominator, then it can go upstairs as a positive exponent. So here's a concrete example. If I have x to the negative third, I do not ever want negative exponents in your final answer, so I would write that as 1 over x to the third power. If I had a problem where the negative power was in the bottom, 2 to the negative third would live as 2 to the third, or 8. So when you simplify using division laws, you want to reduce any coefficient to lowest terms. You want to divide variables by subtracting the exponent, or some of you might refer to it as canceling. You always deal with the exponent on the outside of parentheses first. And do not forget to reciprocate any expression with a negative exponent. Do not leave a negative exponent in any answer. You have a couple of other laws. One we don't use that much, but I feel compelled for your tax dollars to make sure that we talk about it. If you have the absolute value of a squared on the inside, you can think of it as the absolute value of a squared on the outside. And ultimately, because that a, regardless if it's negative or positive, is going to be squared, it just will be a squared. So here's a concrete example. If I gave you 5 squared, it's equal to the absolute value of 5 squared. And that is just equal to 5 squared, or 25. Now let's look at the following law. A to the 0 is equal to 1. Any base to the 0 power is 1. So if I take NOP and raise it to the 0 power, it is 1. If I take 3,000 to the 0 power, it is what? I heard you. 1. If I take negative 6.245785 and I raise it to the 0 power, what is it? 1. Why is this true? Well, if I think of it like this, here's the number 1. I can talk about the number 1 in a variety of ways. I could talk about it as 1 over 1, 2 over 2, 7 over 7, NOP over NOP, any number over itself. So what I've done here is I have given you a concrete example of a base of 5. 5 to the third over 5 to the third. That is a way to represent 1. Below it, I have a general case. I could talk about b to the x over b to the x, another way to represent 1. Well, if I use my properties of exponents, then I am allowed to write the base once and subtract the exponents. Regardless, if I take a concrete example like 5 to the 3 minus 3, or if I take a general case that works for all numbers, b to the x minus x, I end up with a 0 power. And remember how I started with the number 1? So any base raised to the 0 power is 1. And here are some examples. Let's look at number 1. If I have negative 3ab to the 4th, and this is a multiplication problem, times 4ab to the negative third, the first thing I'm going to do is multiply the coefficients negative 3 and 4 to get negative 12. Then I can look at a. Each of the a's have a power of 1, and my properties of exponents tell me when I have the same base and I'm multiplying, I add the exponents. The same is true for b. I have two bases that are, I have the same base raised to two different exponents, so I add the exponents. So my final answer is negative 12a squared b to the first power. I did write the double negatives on purpose for the purposes of teaching. Obviously, you don't have to really write 4 plus negative 3, but I just wanted to be clear in what I was doing. All right, let's look at example 2. On example 2, this is another multiplication law where you need to remember that every term inside the parentheses gets the power of 3. I deal with that exponent on the outside first. So 2 will get a power of 3. X gets a power of 3. Y squared gets a power of 3. 2 to the third can be simplified to 8. X to the third can be simplified to be x to the third. But y squared to the third power is another property of exponents. I have my exponents stacked. So I multiply those to become y to the sixth, and my final answer is 8x to the third, y to the sixth. Moving on to problem 3. This one is actually fairly easy. If I look at 3a times the quantity negative 4a squared, all raised to the 0 power, I look at any exponents on the outside first. What is important, however, is the 0 power only applies to the inside. Anything to the 0 power is 1. So essentially, this is 3a times 1, which is 3a. Let's look at example 4, where I have 5x cubed over y, all raised to the second power. Every term inside the parentheses gets the power of 2. We always take care of exponents or powers on the outside of the parentheses first. So 5 gets the power of 2, x cubed gets the power of 2, and y gets the power of 2. I can simplify the 5 squared to be 25, and I simplify the x. Since I have a power to a power, I multiply those exponents. So my final answer is, and here's the last set of examples. On number 5, when I see a negative exponent, when I see x to the negative 1, it is not negative x. I cannot stress that enough. It doesn't mean my answer is negative. When you have a negative located in the exponent, this implies it is a reciprocal. So I would rewrite x to the negative first as 1 over x to the first, and I no longer have any negative exponents in my answer. In problem 6, the reason I'm presenting this example is the negative 2 is only on the base of x. It is not on the 3. So it doesn't mean that everything in the denominator moves up. The 1/3 stays the same. 1 is to the first power, 3 is to the first power, but x to the negative 2 can reciprocate to the numerator as a positive power. Let's look at 7. Please bear with me as I'd like to show you 2 different approaches in simplifying this particular expression. What I can do first is I can simplify 12 over 4 to get 3. Then if I apply properties of exponents, since I am dividing a to the third over a to the negative second, then I would subtract the exponents. So I would get double signs. It would be 3 minus a negative 2. I would do the same thing for the b family. Since I'm dividing the bases, I would subtract the exponents, which yields negative 4 subtract 1. Now, when I simplify those exponents, 3 minus a negative 2 is 5. Negative 4 minus 1 is negative 5, but I do not want any negative exponents in your final answer. 3 does not have a negative exponent attached to it. A to the 5th, 5 is a positive exponent. They stay in the numerator. But b to the negative 5th would move to the denominator for my final answer of 3a to the 5th, b to the 5th. Here is a second way to get that same answer. One is not better or more efficient than the other. It just is how you might think differently. And there's probably other ways that you could think about this problem, but these are the 2 most common that I find. All right, when I'm doing this, what some students do is they get rid of the negative exponents to begin with. So they just completely rewrite the problem using positive exponents. So the 12 a to the third stays on top, but then a to the negative second would move to the numerator as a positive exponent. B to the negative fourth would go to the bottom or the denominator as a positive exponent. And then the 4 and the b stay in the denominator because they don't have any negative exponents. I don't have to reciprocate them. Next, I can use my properties of exponents where I would add the exponents because a to the third times a squared is the same base being multiplied with different exponents. So my multiplication rule tells me to add the exponents. It is the same rule in the denominator. When I have b times b to the fourth, I have the same base raised to different exponents, so you add the exponents. And in the last step, 12 divided by 4 is 3, a to the 5th is in the numerator, and b to the 5th is in the denominator. For our last example, I have a quotient raised to the negative second power. Again, I want to show you two ways to do this. This is my favorite way to do it. I think it's kind of slick, but I have another way to show you with a little bit more steps. I like to deal with the fact that there is a negative exponent on the outside. I'm going to deal with that negative first. If you think about that a negative means to reciprocate, I can make this negative 2 into a positive 2 power by reciprocating the fraction. So I can rewrite this as the reciprocal of 3x squared over y as y in the numerator over 3x squared, and then have it raised to the second power. So I took care of the negative exponent. Now every term inside that quotient gets the power of 2. Y gets the power of 2, 3 gets the power of 2, x squared gets the power of 2. Since I have a power to a power, I multiply the exponents, and 3 squared becomes 9, for a final answer of y squared over 9x to the 4th. Here's an alternative way to do the exact same problem. Some people want to give every term its negative exponent first. So I've given negative 3 a negative exponent of, or the negative exponent of 2. X squared is a negative exponent of 2. And then I gave y the exponent of negative 2. When I take x squared raised to the negative second power, that is a power to a power, which yields 3 to the negative second, x to the negative fourth, y to the negative second. And now I reciprocate. So the difference between the two methods is I reciprocated first on the first method. I'm reciprocating last here. So 3 to the negative second power becomes 9 in the denominator, which is 3 squared. X to the negative fourth becomes x to the positive fourth in the denominator. And y to the negative second becomes y squared in the numerator. Your learning opportunity is worksheet P2. It also says 5-2. You are welcome to start ahead of the game, especially if you have time, and print it on your own. It's available on the Google Calendar. I will give you a paper copy in class on Tuesday. But just so you're aware, I am going to teach on Tuesday, and then on the late arrival day on Wednesday, I will give you time to do both assignments. Again, to be clear, there's a worksheet for exponents and an additional assignment that I will give you on Tuesday. So please use your time management skills effectively. All of this is due by Thursday of this week, where you will have a daily assessment over this assignment. Have a good day.